We're going to find the derivative of each of the following using good derivative notation. Part A, y equals 5x to the 8th minus 3x to the 7th plus 2x squared minus x plus 9. That is a polynomial, so I can just use the power rule on each term. So I have y prime, the derivative, is equal to, bring down the 8 times the 5 is 40x to the 7th minus 21x to the 6th plus 4x minus 1. Derivative of the 9 is 0, so I don't even write that down. For part B, I have y equals sine x over 1 plus cosine x. Simplify the final answer. So I could write y prime or dy dx, just to practice another notation. Dy dx is the denominator. I'm using the quotient rule here. Denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. And then I'm just going to simplify. So this becomes cosine x plus cosine squared x plus sine squared x all over 1 plus cosine x squared. Now, you might remember the trig identity, sine squared plus cosine squared is 1. That all just simplifies to 1. And I'm running out of room. I'll write it over here. Okay, so this becomes cosine x plus 1 over cosine x plus 1 squared. So the square is going to cancel with that. And I have 1 over cosine x plus 1. Okay, part C. G of x is x cubed times ln x. So that is a product. I'm going to use the product rule. G prime of x is first times the derivative of the second plus the second times the derivative of the first. And then I can just simplify the x cubed times 1 over x becomes x squared. And the second term I can't simplify. It's just 3x squared ln x. Part D, h of x is e to the x cubed ln x. So I should notice that x cubed ln x, which is my exponent here, is the problem I just solved, right, in part C. So this is a chain rule problem that's e to some stuff. So h prime of x is going to be e to that stuff times the derivative of the stuff. And I happen to know the derivative of x cubed ln x from the answer to the previous problem. So this is going to be e to the x cubed ln x times the answer to the previous problem, which was x squared plus 3x squared ln x. Okay, I have a quadratic function, f of x. I want to find the global maximum and global maximum value between -2 and 4. So use calculus techniques, not your calculator. So I'm not going to look at a graph of this function and find its maximum value. I want to use calculus, and I know maximum values could occur at the endpoints -2 or 4, or at a critical point, right? A critical point between -2 and 4. So critical points happen when the derivative equals 0 or is undefined. So my derivative, f prime of x, is -6x plus 12. I want to know when that is equal to 0. Since it's a line, it's never undefined, so I don't have to worry about undefined. Just set it equal to 0, and I get x equals 2. So that's what I'm going to put here, the critical point, x equals 2. And now I need to just know the y value of each of these, at each of these x values of f, the original function f, not the derivative. So I'm going to plug each of these x values into the original function f, negative 3x squared plus 12x plus 7. So when I put in a negative 2, I get negative 3 times 4 is negative 12, minus 24 plus 7. So it's negative 36 plus 7 is negative 29. When I plug in a 2, I get negative 12 plus 24 plus 7. So negative 12 plus 24 is 12, plus 7 is 19. And when I plug in a 4, let's see, 4 squared is 16 times 3 is negative 48. And 12 times 4 is positive 48 plus 7, so I get 7. All right, so if I'm looking for the global maximum, I'm looking for the largest y value on the interval negative 2 to 4. So that would be at 19. So this is the point, that point 2 comma 19 is the one I'm looking for. So I'm just going to fill out this information here. The maximum value of f is 19, and it occurs at x equals 2. The minimum value of f, so that's the smallest y value on that interval, that's negative 29, and it occurs at an x value of negative 2. Okay, now we're going to interpret some derivatives using complete sentences. W equals f of x is the average mass in kilograms of an oak tree that is x meters tall. So my input is the height of the tree in meters, and the output W is the mass in kilograms. So the units on f prime of x, because f prime, the derivative, is the slope of a tangent line, you would calculate that or estimate it by doing change in y over change in x. So my units are going to be y units over x units. So my y units are kilograms, and my x units are meters. So the units can really help when they're asking us to interpret a function notation statement. F prime of 10 equals 347. So my 10 is the same input as it is for f. It's the same x that you put into f that you put into f prime. So that 10 is the height of the tree. So this says when a tree is 10 meters tall, so that's the input, the 10 meters tall, 347 is the output of the derivative, so that 347 has units kilograms per meter. So that says that the tree is gaining mass at a rate of 347 kilograms per meter. Would you expect f prime of 5 to be more or less than f prime of 7? Okay, so we're thinking about a 5 meter tall tree versus a 7 meter tall tree, and which one would be gaining mass at a faster rate as it grows? So f prime of 5, its next meter is going to gain some certain amount of mass. And f prime of, and for a tree that is 7 meters tall, its next meter is going to gain some amount of mass. So almost certainly a 7 meter tall tree is thicker than a 5 meter tall tree. And so if we add a meter to a 7 meter tall tree, it's going to gain more mass than a 5 meter tall tree would when we add a meter, because the 7-foot tall tree is also has greater diameter. So I think that f prime of 7 is going to be greater than f prime of 5. C equals f of t is the cost in dollars to heat a house when the average outdoor temperature is T degrees Celsius. So again, if I want to know the units on C prime, I would calculate it by doing change in C over change in T, output over input. So the units on that would be, my C units is cost in dollars, and my T units are degrees Celsius, so dollars per degree. Do you think C prime of 5 is positive or negative? All right, so this is the rate of change of cost. So let's see, I want to think about what would happen if I increase the temperature by 1 degree. If I go from 5 degrees to 6 degrees, I want to think about, is the cost function increasing or decreasing? So if I have C of 5 compared to C of 6, right? So the cost when the temperature outside is 5 degrees compared to the cost when the temperature outside is 6 degrees. So the cost for 6 degrees should be less than that of the cost for 5 degrees. When the temperature is warmer, it should cost less to heat your home. So that means that the cost function is decreasing. From 5 to 6, the cost goes down. So if the cost function is decreasing, that means that the derivative of the cost function should be negative. Okay, last really long problem here. Where is F increasing? So this is a picture of F. It didn't come out that great on my printout, but your printout should be okay. Where is F increasing? So this is a graph of F. So any place that we are climbing a hill as we read from left to right. So it would be negative infinity until this maximum point at B. Union, then it starts increasing again from D to F. Union H to infinity. Where are the points of inflection on F? So those are places where the graph changes concavity, down to up or up to down. So that would be here at C, E, and G. Identify local extrema of F. Those are maximums and minimums, and they just want the x coordinates. So I have a maximum here, minimum here, maximum, minimum. So I'm going to list the x coordinates of all 4 of those extrema. So that would be B, D, F, and H. Okay, the global extrema on the interval C to J. I want the x coordinates. So I'm looking between C and J. The global extrema, so I want the highest point and the lowest point. So my x coordinate of the highest point is I, or no, it looks like J. This is the highest point on that entire interval, happens at J. And the lowest point on that entire interval happens here at D. Where is f prime positive? The derivative of a function is positive whenever the function is increasing. So I can say C part A here. Right? Function's derivative is positive whenever the function is increasing. Where is f prime equal to 0? That happens at the extrema. So the local extrema of f was part C, so I can say C part C, because that at local extrema, maxes and mins, you have a horizontal tangent line. That means the derivative is 0, because a horizontal tangent line has a slope of 0. Where is f double prime 0? That happens at points of inflection. So C, E, and G, C part B. Where is f double prime negative? So that is where the graph is concave down. A function's second derivative is negative when the function is concave down. So I want to look for places on the graph that are concave down, like a frown. So that is one. That's all concave down. Then we're up, 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 down, and the rest is up. So my intervals where the graph is concave down would be -infinity to C, and then again E to G. And where is F concave up? The remaining intervals. So that would be C to E and G to infinity. What can you say about the sign of F of E? So I want they're asking me about the original function F. Is it positive or negative at E, the Y value? So this point right here, it's below the x-axis, so it is negative. How about the sign of F prime of E? So that we're looking at the slope of the tangent line at E because it's the derivative. That tangent line has a positive slope, so F prime of E is positive. The sign of F double prime of E, there we're looking at the concavity. Is it concave up or concave down? And it turns out that E is a point of inflection, so F double prime of E is 0. The sign of F triple prime of B, that we can't answer because when we look at the graph of F, we can tell things about the first derivative based on whether F is increasing or decreasing. We can tell things about the second derivative based on whether the function F is concave up or concave down, but there's no obvious way to think about, to see the third derivative in the original graph of F. So we say cannot be determined. To sketch the graphs of F prime and F on the axes above. All right, so to sketch F prime, I am going to first identify the places where F prime is 0. Those are my horizontal tangent lines. So in those locations, I'm going to have zeros for the derivative. So my derivative will be 0 at B, at D, at F, and at H. I think I'm going to use another color here. They're hard to see. B, D, F, and H are zeros. And now I just have to look at the sign of the derivative before and between each of these zeros. So before B, I'm looking at the tangent lines on the graph of F. They are all positive, which means that the derivative has to be above the x-axis. Okay. And then between B and D, if I draw tangent lines, they are all negative slopes. So that means that between B and D, the derivative is negative or below the x-axis. So something like that, below the x-axis. And then between D and F, when I draw tangent lines, they are all positive, positively sloped. So between D and F, my derivative is positive, meaning above the x-axis. And then between F and H, the tangent lines all have negative slope, so we're below the x-axis. And then from H onward, my tangent lines are all positively sloped, so it goes up like that, above the x-axis. So that one is F prime. And then I can use F prime to draw F double prime. So I want to look at places where F prime has a horizontal tangent line. So that looks like it happens at C and E and G. And then I'm going to do the same little game with the slopes. So before C, if I draw tangent lines on F prime, they're all negatively sloped, which means that the second derivative, F double prime, has to be below the x-axis. And then between C and E, my tangent lines on the pink graph all have positive slope, so I'm above the x-axis. And then negative slopes, so below. And then finally, positive slopes, so above. So this one is F double prime.